So currently the calculator that I have here is in the radian mode. Now, this is significant for the following reason. If we try to perform a, let's say we try to evaluate sine for 45 degrees. This actually won't work. It won't give us an accurate answer because it's thinking that the angle that we're putting in is using the radian measuring system. So if we want to get an accurate representation of 45 degrees and not 45 radians, then we actually need to change that from radian to degree. So, in other words, if we want to use degrees in our trigonometric ratios, we have to first convert the calculator. So, press your little dock button up here, just here. Go down to settings and status, and then document settings. So that's doc 7.2. What do we see about the second input there? It says radian. Let's bring down that drop box and change that to degree.
Are we gonna have to change this every single time?
Yeah.
Oh.
Yeah.
What's a gradient degree?
Pardon?
What's a gradient?
Gradient. Oh, it's something different. Won't be using that. So let's just try this same calculation again. All right. So that actually gives us something a little bit more useful. All right. Now let's just change that back to, so document settings, and change it back to radian. All right. So let's have a look at 14b, please. Make sure you got your notes in front of you. Okay. What we're going to do is we are going to define the sine and cosine functions. As well as that, we're going to explore their periodic nature. And hopefully at the end of today, we can define them ourselves, or in other words, we know where they came from. And we can evaluate equivalent expressions using sine and cosine. So to kind of give us a bit of an idea of what I'm talking about, let's have a look at this little GIF. All right. So this is a unit circle here. What's happening?
We're going around.
What do the red and the green represent? One question at a time. What does the green line here and corresponding green line there represent?
The Y.
The Y value, which is, I heard it, someone mentioned it, which is our sine function. What is this red line here representing? Cosine, or our x coordinate of this moving right angled triangle. So wherever this position is on the unit circle, it's tracing out a triangle, a right angled triangle, for the corresponding alpha angle here. And the triangle has a corresponding x and y coordinate, which oscillate between -1 and 1, depending on the angle, and -1 and 1, depending on the angle. Now, how this looks like over a certain period is this function or this graph here. That at 0 degrees in the unit circle, let's just wait for it to come back around. At 0 degrees, the vertical position is 0. So starting at 0, the sine function goes up to 1, back down through 0 at pi degrees, down to -1 at 3 pi on 2, and then up to 2 pi. And the cosine function, wait till we get to the angle of 0 again, starts at a value of 1, down to 0, down to -1 at pi, back to 0, and then back up to 1. So that's how our graphs of our functions look like. What could we say about the two functions? It's a pretty ambiguous question. But could we say that they're the same?
Yes.
Yeah. What? How would we describe them as the same then?
Would you say congruent? Was that?
I think you're on the right track. But if we say translated this red one this way, pi on 2, would that then be the same function?
No.
Would this line, this red line,
You added pi on 2 to every equation.
no, just to the cosine one, just
Yeah,
the cosine
yeah.
one, would it be exactly the same?
Yeah.
Yes.
Yeah.
So that's what we'll get at in graphing a little bit, but just in this introduction, we want to see that they both represent the same shape of graph. So, now that we've had a quick snapshot of what they look like, let's look at formally defining them. As we know, the sine trigonometric ratio is defined as the opposite over the hypotenuse, or the ratio of those two sides, and the cosine is defined as the ratio of the adjacent side over our hypotenuse. The consequences of these are that in the unit circle, the hypotenuse of the triangle is always, this hypotenuse here is always 1, which means that our sine function for the unit circle, sine of whatever angle is given, is equal to the y coordinate. And similarly, the cosine function for the unit circle has a hypotenuse which is always 1, which means that the translational horizontal distance x is given by cos of whatever angle is given to us. So, in other words, with an angle here, we can use the cos of whatever angle is here to give us our x coordinate. And likewise for y, we can use that angle and the sine function to give us our y coordinate. And that's pretty powerful. So, let's look at using a unit circle to find or evaluate these 1, 2, 3, 4, 5, 6, and then these 3 down here. So I want you to draw a very quick unit circle. Very quick. Doesn't need to be perfect. Okay, yeah. And I want you to label the four axes here, or the axes arrowheads, in terms of radians. So if that was 90 degrees, let's label them once again in terms of radians. So pi over 2, and then the next 3. Okay, so now that we've got our little guide here, we're going to use this to evaluate these 1, 2, 3, 4, 5, 6. So, find sin of pi on 2. What? Pardon?
Sin 90?
Yeah, without the calculator.
No.
Well, sin is the x or the y coordinate?
Y.
The y coordinate. So at pi on 2, which is here,
Yeah.
the y coordinate is
1.
1.
Okay.
So sin pi on 2 equals 1. Cos pi on 2. So at that same angle, what is the x coordinate?
0.
0. sine of 3 pi on 2. So -1. We're asking for the y coordinate at an angle of 3 pi on 2, or 270 degrees. -1, which is from down here. Cos of 2 pi. 1. Very good. Sine of -pi. So, we mentioned it, I really only touched on it briefly in the last introduction. But negative angles, instead of sweeping anti-clockwise, we sweep clockwise. So we could say that an angle of -pi in this direction is the same as sine of +pi, which has a y coordinate of 0. And lastly, cos of -3 pi on 2. So if we sweep an angle of 3 pi on 2 in the clockwise direction, we end up at pi over 2. So we could say that cos -3 pi on 2 is the same as cos of pi on 2, which is 0. The x coordinate at this point here is 0. All right. Okay, so now we come into the kind of starting to touch on the symmetry properties of circular functions. What can we say about 27 pi? What does it actually mean? It means that we've rotated through 2 pi, 4 pi, 6 pi, 8 pi, 10 pi, all the way through to 26 pi, which we know is a factor of 2, or multiple of 2 I should say, which means that 26 pi is going to be all the way here, and then we've got an extra pi. So this we can break down into a multiple of 2, so that's the same as sine of 26 pi plus 1 pi. And we know that 26 pi as 2 pi, we get starting from here. So this is the same as sine of pi. And then sine of pi is the y coordinate at this position, 0. What about this guy here? Does anyone want to have a go?
It's in the second quadrant on the circle.
No,
Is it 1?
it's not 1. Well, let's break down the fraction first. 11 over 2, as in decimal form, 5.5. So we've got 5.5 pi. So 5 pi is exactly 1 pi more than 4. So let's say this is cos of 4 pi, which 4 pi we know is going to be right back to the beginning again, plus 1.5, which is, in terms of pi? 3. Yep, 3 pi over 2. Excellent. So this is the same as cos of 3 pi over 2, or the x coordinate at 3 pi over 2. Once again, 0. Sorry for those watching on the video, hopefully you can read my writing. I'm getting to the bottom of the iPad. Okay, so our last example here, cos of 55 pi. We could break this up into,
54
yep,
plus 54
and
pi.
pi. So this could be the same as cos of pi. Cos of pi, -1. Okay. And there we've defined where sine and cosine come from using the unit circle, and also how we can evaluate these radians, these radian angles of pi